I'm interested in gravity because it shapes the most extreme objects in the universe. And I spent most of my career working with a large international team on a project that, if you think a little bit about it, doesn't make any sense. I mean, it's crazy, can't possibly work. So in a nutshell, it consists of doing the following experiment. Place two chunks of glass, let's say a kilometer apart. Place another chunk of glass at 90 degrees. Engineer the system in such a way that they can move freely as possible. And then try to measure the relative separation between these objects. It's a very simple experiment, and I'm sure you'll think, well, it's very dull. But what we want to do is to measure this to a precision of better than 1,000th of the size of a proton. If you do not know what this number is, well, let's just say that it's a very, very small number, and here it goes. So it's crazy, it can't work. You may also wonder, why should we do this? And the reason is that this is a method that could allow you to discover some of the most extreme objects in the universe. Objects that we cannot see, that nobody has seen, and that nobody will ever see. So I've asked myself many times why I ended up doing this, and the true answer is that I really don't know, okay? I think the only viable explanation I have goes back to memories of my childhood and adolescence. And I had a huge admiration for people that would try to challenge limits, try to break boundaries. And I'm not talking about science. Science wasn't on my mind. I'm talking about pretty much anything. I'm sure sports is what I wanted to do. But, you know, through some very complicated path that only maybe now starts to make sense, I tried to find a job in which, in my little world, with my very limited abilities, every day I could try to push the limit a little bit more. And I was lucky to end up working on one of the most ambitious science projects of recent years. So the story I want to tell you lasts over a century, and decades after decades is a story of challenging limits, common wisdoms, and pushing boundaries. I think you all know Isaac Newton. He's one of the giants of physics. His theory of gravity was the theory of gravity, and we all sweat blood at school learning it. However, a century ago, a young physicist, Albert Einstein, came along, looked at the theory with fresh eyes, and realized that things didn't quite add up, if ever so slightly. Now, challenging Newton's idea was unimaginable, okay? But now we know that Newton's theory is just an approximation of a more general theory that we call Einstein's theory of general relativity. And one of the great revolutions that theory brought was the realization that gravity has its own language, its own broadcasting channel, through a form of radiation that is called gravitational waves. Now, every object that moves, my arms here, or objects in the distant universe, they radiate little ripples in the fabric of space and time that propagates at the speed of light through the entire universe. And they carry a full message about the source that generated them. This is a fundamental prediction of Einstein's theory. However, Einstein famously said, well, forget about gravitational waves, okay? You will never be able to detect them. They are way too weak. But during the different centuries, the different decades, people started really to think about finding methods of detecting gravitational waves. And the reason is twofold. First one, if you detect gravitational waves, you provide a confirmation of a fundamental prediction of a theory that is a pillar of modern physics. Second, and possibly most importantly, or more importantly, you have a new way of discovering objects that you cannot see. Now, think about how we know what we know about the universe. We look, admittedly with very powerful instruments, telescopes, but we just look. What if there is stuff out there, and we know there must be, that doesn't emit any light? Contrast that with the way in which we have learned everything around us. So we look, we hear, we taste, we touch, we smell. We have a sense for every channel of information. Think about going to a wonderful 3-star Michelin restaurant and enjoying the delicious food by watching it. Or going to an Adele's concert, not being able to hear her song, just looking at her. What would we miss? So what are we missing by just looking at the universe and not being able to tune on a new broadcasting channel? So how could we observe gravitational waves? Now, gravitational waves that travel through this hole, when I move my arms, for example, okay, they stretch and squeeze space and time. Your body is really being stretched and squashed by gravitational waves, but you don't feel it. You don't feel it because it's such a tiny, tiny, tiny effect. But in order to observe them, what we need is a measuring device that measures displacement. Okay? So we need a ruler. But not any ruler, a super ruler. Now maybe those chunks of glass starts to make sense. And remarkably enough, we've been able to design such a ruler. It's called a laser interferometer. It uses light as a ruler. So this is LIGO, the Laser Interferometer Gravitational Wave Observatory. It actually consists of 2 identical instruments, one in the swamp of Louisiana at Livingston, and the other one in the desert of Washington State at Hanford. A laser beam shines through a piece of glass, the beam splitter. It's divided up into 2 arms. It travels 4 kilometers. It reaches 2 other chunks of glass, the end mirrors. It bounces off. It comes back. It then gets recombined at the beam splitter. And by watching the change in the intensity of light, we can measure these very, very minute changes in distances in the arms to better than 1,000th of the size of a proton. So LIGO was conceived many years ago, and it took over 30 years really to conceive, design, build, and now operate this instrument, and the effort of over 1,000 scientists and engineers. And LIGO was completed about a year and a half ago, and it started to observe the Saturday, the 12th of September, 2015. It monitors the old sky, and we didn't know how long we would have to wait to detect gravitational waves, maybe forever. 2 days later, it's Monday, September 14th. This is what shows up on our computer screens. It's the same signal that arrives first at Livingston, 7 milliseconds later arrives at Hanford. It has a very peculiar structure of a signal that increases in frequency and in amplitude and then disappears. It is a signal that you would expect from gravitational waves from a binary system. And the reaction by me and everybody on the analysis team was, this is a joke, okay? This just can't be real. Something is wrong. And the name of the game became to try to figure out what is the source, maybe local, man-made, or around us, that has produced this signal. And it took months to figure it out. And as Arthur Conan Doyle said, when you have eliminated the impossible, whatever remains, however implausible, must be the truth. And what remained was the only explanation that this signal was really due to gravitational waves that wiggled the LIGO mirrors from an astrophysical source. And what a source! So about 1 billion years ago, two black holes, the size of about 200 kilometers, is the size between Warwick and London, roughly. One packed with 29 times the mass of the sun, the other one packed with 35 times the mass of the sun, were orbiting around each other at half of the speed of light, 150 million kilometers per second, okay? Their separation was about the size of the UK, a bit more. So if you have troubles in picturing this, think about this. So these two black holes were orbiting around each other with a frequency of a kitchen mixer, okay? 50 to 100 times per second. LIGO saw the final quarter of a second of this motion, 5 orbits. The system lost more and more energy, and then they smashed into each other. In this process, they released the equivalent of 3 times the mass of the sun into energy. How much is this? It's enormous, okay? For a fraction of a second, they emitted more energy than all the energies that goes in light from all the stars of all the galaxies in the entire universe. So nobody saw a flash of light, because all the energy got pumped into gravitational waves and the fabric of space-time. It traveled 1 billion years. It arrived here on that Monday morning and wiggled the LIGO mirrors. So this very unremarkable wiggle is the fingerprint of the last quarter of a second of the swan song of a binary black hole merging and forming the first cry of a newborn black hole. This is 3 discoveries in one. Is the detection of gravitational waves 100 years after Einstein predicted them. It's the discovery of objects we never saw before, binary black holes. It is the best evidence we have today that these object black holes that are objects of the theory, objects of mathematics, actually are produced by nature. But the story repeated itself. So we didn't see only one. In October 12th, we saw another characteristic signal, this time from 2 black holes, one of 23 and the other one of 13 solar masses. Is not as strong, we cannot be as sure as the first one, but most likely it is from a binary black holes. And then we had a late Christmas present. On Boxing Day, you cannot see on the plot because it's too weak and you need to use all the sophisticated analysis techniques to pull it out from the data. We detected gravitational waves from a 15 and a 7 solar mass binary black holes. Guess what? The universe is full of binary black holes smashing into each other. We didn't know. It seems that we can estimate, every 15 minutes or so, there are binary black holes that collide in the universe. And so far, we are able to see gravitational waves only from the from the closest objects we have. And in the future, as the instrument becomes better, more instruments joins this network of interferometers, we'll see more and more. So you see, this is really the moment when LIGO started to operate, the moment where we had a device sensitive enough to tune on this new broadcast, we started to discover new things. It's a new era of cosmic exploration. It's like the very first explorers who sailed the oceans. And as they venture past the pillars of Hercules, they discover new lands. Who knows what we're going to discover next? So one day, maybe a distant day, a day that I won't see, we will take the ultimate map of the place we live in. A map of the universe, our universe, when it was only a fraction of a second old. And that baby universe has got only one way of talking to us. And that's gravitational waves, nothing else. Of course, you know, this is uncharted territory, and I would be a fool and an arrogant to say what we're going to discover next. I don't know, I cannot know, I just hope to be surprised over and over again. Thank you.